Так, Дмитрий, думаю, можно уже начинать.
Да, добрый вечер. Ну, для меня добрый день, утро точнее. Вот меня зовут Дмитрий. Я сегодня проведу... excuse me, it's supposed to be in English. So, good evening, everyone. My name is Dmitry, and I'm supposed to lead this, not to say presentation, but more like a practical workshop. And just a little bit about myself. I currently live in Mexico for more than 2 years by now. But originally I'm from St. Petersburg in Russia. And I work at Microsoft. So I've been doing software development for more than 20 years by now, and started with .NET development in 2006. So I've tried quite a bit of different types and sorts of .NET applications, but mostly focus on backend services. My current project is related to M365, Microsoft infrastructure, service-to-service communication, and authentication. So for this workshop, we are going to review how we can approach solving algorithmic tasks. And there is a great, very old, but still great book by Donald Knuth. In Russian, it's called Algorithmy плюс структура данных равно программы. I'm not so certain how that book is called in English. It's a large work, and well, it would take quite a bit of time to read it, but still, if you have it, I would highly recommend. But the general message here is that when we are working with any kind of algorithmic tasks, we always need to choose our data structures properly, because sometimes they can just do a lot of required work by their nature, according to what they provide. They can give a very good solution. So for today, we are going to review so-called least recently used cache implementation. Okay, let me start a brief presentation. Just a moment. Okay, for some reason you don't see my screen, please let me know in chat. Otherwise, I'll proceed. So the least recently used cache, or LRU cache, is designed to store items, of course. The cache has limited capacity. It's not indefinite. And the least, so when the capacity is exceeded, and we put a new item into cache, the least, just a second here. So the least recently used item is evicted or removed from the cache. So here we have like our cache in its original state. It has a capacity of 4 items. So it's,
I'm sorry to interrupt you. Can you please turn on the camera for 10 seconds, please?
Sure. Okay. So here is our cache. It has a capacity of 4 items. We stored already 4 items in the cache, and then we are going to store one more item, item 5. So, and if item 4 is the most recently added item, and item 1 is the first added item. So it has the oldest age in the cache. So when we add item 5, we need to remove one of the items and we remove the oldest item. So the item 1 gets evicted from the cache. So after this operation, our cache looks like this. So no more item 1. And when we access an item, like in this case, we start from the same cache condition. So let's say we access item 2. It's not, previously it was not on top of the cache, but as soon as we access it, it's marked as the most recently used, so it gets on top of the cache. So our cache turns into this state. So it's a very, actually, simple task. Well, at least it's easy to understand. But let's review how we can implement it. So let's start with a sample contract of a class that implements LRU cache. And let's review the operations. Well, of course, we need to get an item. We need to hide an item. We may want to remove an item. We may want to clear cache. We may want to get current item count. And we may want to check if a particular item is in the cache or not. So essentially, we have 6 operations to implement. And let's see how this these operations can look in .NET world. So this is, from a certain point of view, this is a typical .NET collection, though it has certain algorithmic specifics. So we can use standard conventions that .NET collections implement. So for getting an, first of all, it would, in most cases, it would be very valid to locate, to store in cache both an item and its key, because an item or an object that we store in cache can be very large, and locating such an object in cache by its value will be a very expensive operation. So it's best to provide a key for such items that's much less costly to compare. So that's why our cache will store item key and item value. Key being a short representation like integer, long, GUID, string, or whatever we may want to implement. So we first have this method, try get value. We provide a key, and we have an out parameter which would return the value. So you may consider ask why not use just get value method that would take a key and return a value. But that method would not give us a clear indication that for the requested key, there is no actually item in the cache, because for some reason our cache may store a null value. So in this case, in order to check if the particular key was actually in the cache, we would need to first call the contains key method. So instead of one operation, we would have to call 2 operations. And try get value solves this by definitely telling us if it was able to retrieve a particular item or not. So then the add method, key value, and a Boolean result. This item was added in the cache or it was already present in the cache. Same remove method with the same conventions. Well, the rest is obvious, clear method and the count property. Okay, let me switch now to my IDE and open a solution. Just a moment. I will also reshare my screen so we can look at IDE. In just a moment, it will load. Sorry about that. I had to switch to a different laptop just before the presentation, so things take a little bit of more time than I would want. Okay. So here we have already prepared solution with all implementations because we have a very limited time for presentation. So fortunately, we don't have time for typing all the code in, but nonetheless. So let's first look at the contract. So I provided this interface, but actually when implementing this code, you don't necessarily need to use interface, but just another overview of the contract. Actually, we see all the same. We will use this interface for unit testing of our solution. But then let's review two different implementation, what I call a naive implementation, very simplistic, and a more complete implementation. So as you remember the diagram, the least recently used cache, as it was shown, looks very much similar to a linked list. So essentially, we have the top of the list, we have the end of the list, and the items are linked to each other. So linked list is a very good way to start our implementation from. So let's look at this naive implementation, and I will explain later why I call it naive, mostly for performance reasons. Okay, so just a second. Okay, so here we have our linked list, and if you see, I'm storing here a cache entry object. Again, it's a generic implementation, so we have our generic type for key and generic type for value. We have certain constraints that the key cannot be null, which is very reasonable requirement, and the value is a class. It does not have to be a class, it can be a struct, but for simplicity, we will keep it a struct. So this cache entry essentially is a simple container. It just takes the key, takes the value, and exposes this as public properties, nothing specific. So then we construct our instance. This is the constructor. It takes a capacity. As we remember, a capacity is a number of items in the cache that cannot be exceeded. So whatever we add over the capacity will cause the eviction of the oldest items. So here we have some small check. If the capacity is unreasonable, we need to throw an exception. So the count item implementation is very straightforward and not really interesting. The question, if this works for absolute beginners. Okay, let me step back a little bit on this. Well, first of all, please free to send questions in chat as we go. I will try to answer them as soon as possible. Then absolute beginners. Well, if you are familiar with basic programming concepts, if you are familiar with .NET development with C# language, yes, you can. I'm sure you can get something useful from this presentation. Otherwise, unfortunately, it may be not as useful, but that's really for you to see. Okay, and let me Okay, I'll try to go into more detail during my presentation. Okay, so now let's review each particular method implementation. So first we would be getting, okay, I hope it's clear what a linked list is. So, but let me repeat. A linked list is essentially a collection of items that stores not actually an item, but a node in the list. And a node has two additional properties besides the item value itself. And these properties point to the previous item in the list and the next item in the list. So if you, for example, imagine people staying in line and holding each other by hands, so you can get a good picture of what linked list is. And additionally, linked list stores the first item in the list and the last item in the list. But having at our disposal any item from the list, we can get to all other items if we navigate properly. So this is our field cache list that is supposed to contain our cached items. So when we are trying to get a value, an item from the cache, we have our key. Here we use a link extension method, first default, that essentially locates an item in the collection using a provided expression. So we are checking if a particular item in the list, its key is equal to the key we provide to the method. So if we found an item, we store its value. Okay, just a second. I think I need to change the way I present. Okay, so if not here, let's look at this one. So if we look at this diagram, we are accessing an item, and because this operation actually changes the age of item in the cache, we need to put this item on top of the cache. So that's what happens here. So we found an item, we remove it from the list, and we add it as first in the list. So essentially, this is the iteration that happens there. Then we stored the item value in our out parameter, when returned true, and the calling code has our item. So it's very simple. If we didn't find an item, we store null and we return false. So it's very straightforward. When we add an item, we first check if this item already exists in the cache. If it exists in the cache, we compare its value just to make sure we don't need to update an item. So if the value equals, we return false, so the item is already in the cache. No need to do anything. So if we found an item, but its value is different, so it means that under this key, we add another item. So essentially, we perform an update operation. So then we remove the specified key from the cache. And then we create a new cache entry object, and we store it in our cache and return true, everything is fine. If we did not find an item, then we need to check for this scenario so that we are not adding more items in the cache than the cache can contain. So we do not exceed the capacity. So we call this private method. And essentially, it performs a loop. So while the cache, the account of items in the cache is at the capacity, it removes the last item. So it doesn't have to be a loop. It's enough just to have a single check with if, because supposedly we never should exceed the capacity more than by one item. So essentially what happens here, we are performing this cache eviction check. So after that, after we evicted optionally the least recently used item, we add an item, everything is fine. Removing an item is very much like getting an item, because first we need to make sure that there is an item in the cache, which we perform using the same operation. If we found it, we remove the item, return true, otherwise we return false. So everything is very straightforward. And last, when we check if the item is present in the cache, we again use a link operation any, which checks if any of the items in our collection satisfy the criteria. And the criteria is key equality. So it's a very simple, but as I said, it's a very naive implementation. So why is it naive? So let's now speak about the big O notation, or in other words, algorithmic complexity. So algorithmic complexity of an operation is essentially can be, well, in terms of big O, we normally have O1. So O1 means that regardless the data size, the operation will only need to execute one abstract operation to achieve the result. Like for example, O1 operation, if we have an array, again, regardless the size, we can get a specific item from an array by using its index very simply. So it's an O1 operation. So if we, for example, have something like this, and then we do this. So accessing an array element by its index is an example of O1 operation. It's very fast, as fast as it can get. So then we have more expensive operations, like for example, ON operations. So ON means that we can achieve the result. The cost of achieving the result depends on the data size we operate on. So if, for example, using the same array, like we, for example, want to check if x equals 5, we return true. Okay. So enumerating an array in this case is an example of ON operation. So let me put the comment here. This is O1, this is ON. So we don't really know if we will find number 5 in this array or where in the array it is located. So this is why the cost of this operation is ON. And then there can be more expensive operations. Like, for example, if we would be doing a loop in a loop, this would be already O square n, even more costly operation that depends on the multiplication of data sizes. So, and of course, the more costly the operation is, the slower our code executes. And again, the more data size we have, the slower our code executes. So in the ideal world, we really would want to have the least expensive operations inside of our code. Now let's look at this implementation and see how it stands in terms of algorithm complexity. So like obviously, like here, we have a O n operation because we need to enumerate the whole cache list in order to find the item that's matching this criteria. And the same stands true for any other of our methods that follows the same approach. So whenever we call try get value, whenever we try to get an item from our cache, it's a ON operation. Whenever we add an item into our cache because it calls into try get value, it's an ON operation. Removal is also ON operation. Actually, in certain cases, this can be like double ON operation. So it's not very bad, but it's also not very good. And again, the cost of using these methods will grow with the size of our underlying collection. So the bigger the size, the more costly it is to use these methods. So what can we do? Kind of again, in terms of algorithmic complexity, the best result we can achieve instead of ON operation, we can use O1 operation. So we need some kind of different data structure here. And let's now move to kind of a more complete implementation of least recently used cache. So it implements the same interface. The reason I wanted to add to have this interface is that to make sure that both implementations follow the same contract by default. So they provide exactly the same behavior, both of them. Just the performance is going to be quite different. So here we have a similar container for our cached items. Just in this case, it's a struct, but I will touch on that later. Now we, in addition to the linked list, we have the dictionary. So, and again, stepping a little back, so a dictionary also stores a key and a value that this key indicates. So a dictionary cannot store multiple values with the same key. The key is unique. So, and dictionary actually provides O1. So when we want to get an item from the dictionary by its key, the cost of this operation is O1. And the reason why it happens is that underneath it uses what they normally call hash tables, or like each of these keys. Okay, let's put it this way. So actually each data type in .NET and C# has this method getHashCode. Well, probably you're familiar with it, but if not, let me explain a little deeper here. So this method returns an integer. And this integer is calculated using quite sophisticated but also very fast algorithm that kind of strives to provide a unique representation of the object. So, for example, like capacity, it's an integer value, integer variable. Also has this hash code. So they different data types implement the hash code calculation differently. So, but the goal again is to make it as effective and as unique as possible. So what dictionary does, it actually has, well, in a very simplistic way, it has an array, and simple array, and it has let's say hash distribution function that so when we add an item into a dictionary, essentially first thing it does, it calculates the hash code, then it applies this hash distribution function to the calculated hash code, and it sees where this particular hash code belongs inside the array. So let's say we have an array of 64 elements, something like, for simplicity, something like that. Yes, then we get our hash code. Then we apply this hash code distribution function to get the index in this array. So, well, of course, it's not just an integer array, it's a more complex structure that's also designed to store the values in our dictionary. So once we have a dictionary, we store in this array the required value. And the same way, when we are retrieving a value, we calculate the item hash code, we apply the hash code distribution function. So we essentially transform the item into its index in this internal array. Of course, this the real implementation is a bit more complex because there can be hash code collisions, like completely different objects may produce the same hash code. But in this case, the algorithm also solves it in a very efficient way. So this is why, kind of long story short, this is why dictionary provides the O1 operation on item retrieval or adding, whatever item operation we have on a dictionary. It's a very fast operation. So instead of storing all our items in a linked list, we now store them in a dictionary that provides very fast access to the item value by its key. We still maintain the linked list, so we need to provide the same behavior. Like we need to know what's on top of our cache, what's at the bottom of our cache, and how the items are linked to each other in terms of their age. So now when we get an item, we have an O1 operation. And okay, let's just mark. This is actually an O n operation. This is O1 operation. So like if our naive implementation had 2 ONs and 1 O1, then our improved implementation has just 1 ON and 201. So we kind of doubled the performance of the worst case scenario for this operation. Why this is still ON? Because we are locating an item in a collection. So we need to enumerate the collection in order to find the particular item. But in turn, this change of algorithmic complexity affects the whole set of our operations. Like the add operation becomes equally faster, and so on. Also, the eviction operation becomes faster because, no, the eviction operation remains the same, sorry. But let's see how these changes translate into real numbers. Okay, something happened with my NuGet package cache. So never mind the red mark, so we are not going to compile it. And by the way, the code from this presentation will be available in an online repository. So I will send the link later, so you will be able to download it, run, and explore. So here we have a benchmarking project that essentially what it does, it uses either naive implementation or the default implementation. Kind of the keys are integers, the values are strings. So we run it for two different capacity values, 1,000 and 10,000 items in the cache, and we add like double of the capacity. So it means that kind of we'll have to do a lot of item lookups inside the cache. We have to do a lot of evictions and so on. So we will be using our cache very heavily. So both for naive implementation and for the default implementation. Also, like to give a better overview, here we will be using a string key. Strings as keys are more expensive, slightly more expensive, but nonetheless. And so here are the results. So if we can see, the naive implementation takes much longer than the kind of typical implementation, the proper implementation. And the reason why it happens is exactly the difference of algorithmic complexities. And so if you remember here, a lot of operations use ON complexity. And again, because here we'll run it in a loop, this ON complexity becomes square kind of complexity. So we need to multiply it. So the actual number of operations required to execute this benchmark is like much higher. It's not like so it's a square. While in this case, the actual number of operations is much lower because we do not calculate kind of the complexity of this code doesn't become ON square. So this little exercise, and I hope gives you a good incentive to look at the algorithmic complexity of your code and try to find a less expensive approach to it. Okay, we are doing with time quite well. I want also to cover some unit testing specifics, but let's take a little pause and see if you have any questions before we move to unit testing. You can send them into chat. I'll start with the unit testing, but please do not hesitate to send your questions because it may take time to type them in. Okay, so for unit and if you are curious about what you need to benchmark your application, just a second. So here is this NuGet package, benchmark.net, which provides, you can call it kind of industry standard for benchmarking.net applications. It's very powerful, very effective, and if you are not familiar with it, but you want to do some benchmarking, you can Google it, find on internet. It has very extensive documentation. It's really very convenient to use. Then before moving to unit tests, let's look at these two packages first. We will be using XUnit. As you might know, there are a few different unit testing frameworks for .NET, NUnit, XUnit, MS tests, a few others. But in this particular case, we will be using XUnit. And another very helpful package is Fluent Assertions. Well, any unit testing framework provides its own way to check for unit test results, like to assert, as they call it. Fluent Assertions is a kind of standalone assertion package, which can be used with any unit testing framework, and it provides a very, let's say, convenient way of executing assertions in unit tests. Okay, I see there are some questions. Okay, let me just quickly go over them. Okay, from Lena, how can one improve their algorithmic problem-solving skills in practice? Are there specific resources or platforms you would recommend? Well, you might have heard, I'm sure you've heard of LeetCode and other kind of platforms that kind of provide algorithmic tasks, and kind of you can submit your solution and will evaluate them. So this is not actually, this is not what I would recommend. I mean, it's good for self-testing, like, okay, kind of you want a challenge, so you go to LeetCode, you get some tasks, you try to solve them. And it actually may help you by training your mind and kind of improve your skills. So for some people, it actually may be a way to go. At first, it's good to remember these algorithms plus data structures. So as you have seen in this implementation, just by using a proper data structure, we completely changed the performance. We completely changed algorithmic complexity of our solution, right? So essentially, the code is the same. We even have slightly more code, but the algorithmic complexity went down dramatically. So you need to know your data structures. So learn what data structures the standard .NET provides, like hash sets, dictionaries, lists, linked lists, arrays, other types of collections. Also, like, again, I mentioned this extensive algorithmic book on algorithms. And if you have time and curiosity, read it. Otherwise, try to find other resources on internet that give you a brief but good description of existing algorithms. Of course, there are some tasks that require very custom-made approach, like very sophisticated, but most of the tasks can be solved just by combining already existing data structures. Like, for example, .NET has so-called bit array, actually the array of bits. So the elements of these arrays are bits, either 0 or 1. But this structure can be very effective in certain tasks, like if you, let's say, need to calculate some distribution. So again, using the same approach as dictionary has, so it translates a value into an index in its internal array. Bit arrays can be applied the same way. So you can translate a specific item into an index in a bit array and just store there 0 or 1. And it will be very fast then to analyze this bit array after you run your algorithm. So you need to explore. Okay, so let's go to next question by Igor. I have a little question. What precautions need to be taken when using the cache in multi-threaded application? Okay. Okay, and so multi-threaded. So concurrent data access is a very tricky thing. And if the best thing you can do is to avoid concurrent data access. But again, don't take this in the absolute. Reading access is always safe. I mean, you have some data, you can read it safely from as many threads as you can have. Nothing will happen because reading data doesn't change them. The tricky things happens when you need to change the data from multiple threads, and especially if one thread changes the data and other threads read the data. So I recommend you to look at concurrent collections. Again, .NET provides a few collections that are specifically designed and fine-tuned for concurrent data access, like concurrent dictionary, concurrent set, concurrent back. So Igor, if you want to, or anyone else, if you want to explore how to have efficient concurrent data access in multi-threaded applications, I suggest you explore how those collections are implemented. You can look at the source code, you can find very in-depth description on Microsoft.NET blog, official .NET blog by Microsoft. They have like some performance related article series by Stephen Taub and by other Microsoft developers. So they go into deep details there. So next question from Daniel. Can we use LRU cache in different languages? Yes, definitely. And if, again, all these data structures, they are not language specific. Like essentially every mature language has the same data structures. They can call them differently, but they solve the same task. What is the most suitable language? Really, the one you are most comfortable with and the one that your project requires. And does the use of LRU cache affect the complexity of the algorithms? Well, if your algorithm or your task require using a particular data structure, such as LRU cache, then you need to use it. Of course, everything comes at a cost, so nothing is free, right? So like we saw that like here, for example, this is as fast as it can get, this is as fast as it can get, but this still has a cost. And this, even this operation can be potentially further optimized. I will not go into much details now, but the thing is that the linked list actually provides nodes. So for example, if we could store in our dictionary not the cache entry object, but the linked node of cache entry, then removal of linked node from cache list is actually all one operation. So yes, this can be further optimized. Again, but you need to know your data structures in order to kind of affect the effectiveness of your solution. Okay, let's move to unit testing, and we can have a few questions later. Okay, now this worked. Well, let's first look at the interface. So what actually unit test stands for? So we have some code that provides some contract, some behavior. A contract is a behavior. So when we have an interface, we essentially describe how our implementation should behave, what kind of behavior it provides. So when we're implementing unit tests, we essentially want to validate that our implementation indeed provides the behavior we expect from it. So it works when it should work and it fails when it should fail. So very simple idea. And so any particular implementation, and we can start with the constructor. So when we look at the constructor, we see that in certain conditions it can fail. In other conditions, it should not fail, right? So our first unit test method can validate like this. So we create a new instance, we give it a capacity, and we expect that it does not fail, right? So because if, for example, if we give a capacity of 100 and suddenly we had an exception in our program execution, that wouldn't be good, right? So that's exactly what we are validating in this first unit testing method. So we can kind of call it new instance does not throw, and it's good to give a descriptive names to testing methods. So the method name by itself states what it is, what it validates, or what it expects from the implementation we are testing. Of course, we can always write comments, but when we execute our unit tests, we see that this particular method either passed or failed. So we don't actually see the comments in our text. So we see just method succeeded or method failed. And it's good to have a telling name, so we kind of immediately have an idea actually what happened. Okay, then let's go over this. So unit testing methods can be parameterized. Of course, they don't have to be parameterized, but here we essentially what we want to validate is that for any of these capacity numbers, we can successfully create an instance of LRU cache. So here, instead of simply saying you and then calling the constructor directly, I have these generic functions because I wanted to validate both implementations, the naive implementation and non-naive implementation. So, and I did not want to write two unit tests because they would be mirroring each other. But in production code, you would have most likely to write both unit tests. Okay. So here we have a function. As you see, we have a lambda expression here that calls into code we want to validate. And then, so here is our lambda delegate. And then what we apply here is a fluid assertions syntax methods. So essentially, if we just read that action should not throw, right? So it's very descriptive. So fluent assertions will call the action, and this particular assertion expects that this call will not throw an exception. Very telling and very straightforward. And also see, I have these comments, arrange, act, assert. So arrange, act, assert is a kind of, I cannot say it's a paradigm, but normally when you write a unit test, it consists of 3 blocks. Arrange, first you prepare your system under test. You create all required objects, conditions, all that stuff. Then you act, so essentially you invoke the behavior you want to test, and then you assert, you actually validate the results. So, and it's good not to mix those blocks. So first you have all your arrange code, then you have your acting code, and you have your asserting code. And of course, it's good to maintain unit tests short and concise. So, okay, we validated that for these capacity numbers, our constructor does not throw. Then also see that in certain conditions, the constructor throws an exception, right? So we also need to validate that. So we write another unit testing method where we inject invalid capacity numbers. And so essentially we have the same arrange kind of code, but then the assertion code is different. So now we expect that our action executing this delegate will actually throw argument out of range exception. Again, very telling and easy to read. So that's why fluid assertions is very good and widely used. And then we essentially go over all these methods one by one, and we follow the same approach. So like, for example, here I have 3 different methods: add new item, add same item, and add same key, different value, right? So I create, to validate that adding an item works, I create a new instance, which is the arrange block. Then the act block contains that I'm adding an item. I store its result in a variable. And then the assertion block actually validates that this code works according to expectations. So the result, the added variable, should be true, right? And the count of items in the cache should be 1. Again, very simple, very straightforward. Again, when I'm, okay, then that here I added a new item that definitely does not exist in the cache. Here I want to validate how cache the implementation behaves when I'm adding the same item. So the arrange block contains a cache populated with a single item. Then I'm trying to add the same item. And again, the assertion code states that the added variable should be false, and the count of items in the cache should still be 1. It shouldn't be 2. So if it, for some reason it's not 1, we have a problem in our implementation. And then essentially the same approach, adding the item with the same key, but with a different value. So again, assertions, so it all looks very similar. Also, parameterized tests help to kind of reduce the code size for unit tests, because like, for example, taking this example, sorry, taking this unit test method where I'm testing the try get value method. So I test both conditions. So I'm getting existing item from the cache and I'm getting non-existent item from the cache. I could write two different methods, unit test methods, the same way as I've done here. But I can also write a single parameterized method. So I submit the item key I want to check, and I submit the expected result. Instead of two methods, I have just one. Okay. Sorry. Do you hear me?
Да, все слышно.
Okay, sorry about something happened. When did you stop hearing me when I was going over fuels test methods or before that? То есть, когда меня перестало быть слышно?
Вас перестало быть слышно в 20:06. В тот момент вы говорили... Так. Я не вспомню, честно говоря. Сможете показать вот эту панель?
It's something strange. Что-то странное происходит у меня с подключениями. Сейчас, секунду. Okay, in general, this is all I have for today, and we are also already good with time. So if probably now is time for questions, so please type in or voice them. And можно также по-русски для простоты дальше. Мозг как размер кэша для задачи. Опять же, любые данные в памяти – это объем памяти. Да? То есть это управляемая среда исполнения, то есть один из ее основных аспектов как раз управление памятью, автоматическая сборка мусора, все такое. Вместе с тем автоматическая сборка мусора имеет свою специфику. То есть это может быть очень дорогая операция, если мы используем слишком много памяти. То есть тот сценарий, которого мы хотим избежать. Поэтому, когда вы думаете, сколько памяти выделять, также стоит иметь это в области внимания. С другой стороны, кэш – задача специфическая. То есть в кэш мы складываем те данные, которые нам дорого или очень дорого получать иным образом, там, внешнего сервиса, из базы данных, еще как-то. То есть кэш – это своего рода оптимизация доступа к данным. Входит такой фактор, говоря, какова наша операционная нагрузка. Да? То есть, грубо говоря, объем входящих запросов, насколько широка выборка данных. То есть, грубо говоря, если у нас 10 триллионов объектов, и у нас очень много запросов на каждый, в большинстве случаев эти запросы запрашивают разные объекты, кэш нам не поможет. Потому что, грубо говоря, почти каждый запрос будет промахиваться мимо кэша. То есть кэш хорош не для всех случаев жизни. Если у нас запросы повторяющие, но операции с высокой степенью вероятности работают по одним и тем же данным, то кэш это может быть очень выгодно. То есть, вот, к примеру, у нас в процессе аутентикации, авторизации запросов используются разные типы токенов, там, в зависимости от. И по одному типу токенов у нас процент попадания в кэш больше 99, то есть использование кэша очень выгодно. А по другому типу токенов процент попадания меньше 10. Как бы много выгодно, но не очень. Поэтому оптимальный размер кэша зависит от массы факторов. То есть, с одной стороны, это сколько мы можем ему выделить памяти так, чтобы это не вредило производительности приложения. С другой стороны, вот это плотность выборки данных, которая может попасть в кэш. Вопрос от Игоря. Какие метрики наиболее хорошо подойдут для оценки эффективности кэширования? Кэш-хит, кэш-мисс, то есть попадание в кэш, промах мимо кэша. То есть, грубо говоря, процент операций, которые привели к выборке данных из кэша, и процент операций, которые промахнулись мимо кэша. Собственно, все. То есть вопрос в том, как их посчитать, уже зависит от, опять же, конкретного кода. Но в целом подсчет таких метрик можно включить в реализацию самого кэша и уже из него получать эти. Но опять же, здесь могут быть нюансы, потому что опять один кэш может обслуживать разные типы данных. Вот как, например, в нашем случае у нас один кэш на токены, но токены разных типов. И поэтому статистику по эффективности кэширования мы ведем не внутри кэша, а дополнительная, грубо говоря, реализация, которая, так скажем, имеет свой инстанс для каждого типа токена. Спасибо и вам. Да, так, ссылка. Сейчас, секундочку, вышлю ссылку на репозиторий. Сейчас найду ссылку. Так, вот в чат отправляю ссылку на репозиторий, где вот этот код, на который мы сегодня смотрели, есть. То есть две реализации, бенчмарк и юнит-тесты. Ну и также, собственно, PowerPoint вот с этой презентацией. На этом, наверное, закончим. Всего доброго.
Спасибо большое за лекцию.
Пожалуйста.
Думаю, на этом можно завершать.